Hello all, here we are with the lecture number 7 of haloalkanes and haloarenes. So this is the continuous series for 12th standard chemistry, okay, 12th standard chemistry, and this is based on NCERT. Okay, so the 12th standard student, whoever is not going for any coaching classes or they are doing the self-study, so for them it is very helpful because I'm going to provide you all type of concepts. It is like 100% concepts I'm giving you, as well as I'll provide you notes. Okay, so that is also 100%. It is not like that you are going to, again, you have to go for any coaching center or somewhere else. I'm providing everything over here at free of cost. So today's class will continue. Preparation part we have completed. Now this is the physical properties. Okay, so physical properties we'll see. Okay, so in these physical properties, we know that alkyl halide generally, whatever we have seen in your chemistry laboratory, also you will find these chemicals. You won't find, okay, you won't find these chemicals in your practical lab because this is at a gaseous state. Okay, but you will find, okay, but you will find this molecule, I know, CH2, Cl2. This is DCM, short form, the name is DCM. In many industries, they are using dichloromethylene, okay, DCM. Then you will find this also CHCl3. This is nothing but your chloroform. Then you will find CCl4, carbon tetrachloride, correct. So now we are going through with the physical properties. So let us start with this type of molecules only. Then we'll discuss together, and I'll provide you the notes also. So in physical properties, we'll see how the melting point or boiling point trends it's following. See, CS3 in room temperature, it is in a gaseous state. Okay, CS3Br, or if you want, you can take the similar one, CS3Cl, you take it. Okay, so CS3Cl in room temperature, it is gaseous state. As one more chlorine we have added over here, now it is changed to the liquid state. One more chlorine, again it is in liquid state, one more chlorine, it is liquid state. But what is the difference between these three liquid state? So as we know that the molecular weight is increasing, okay, as the molecular weight is increasing, your boiling point will also get increased, correct? So the boil and but there should not be any hydrogen bonding or maybe any type of strong van der Waal interaction. It should not be present. Then only if see for the in this case here also no hydrogen bonding, here also no hydrogen bonding. In this four molecule we don't have any hydrogen bonding kind of thing. So whatever is there is that will be depend on molecular weight. Okay. So as we increase in chlorine, the molecular weight is increasing. So the boiling point trends will also get increased. So as we see the boiling point trend here, it will be CH3Cl, then it will be CH2Cl2, then it will be CHCl3, then it will be CCl4. And in your lab, like I have started with your chemistry lab, right? So in your chemistry lab, you will find this one, you'll find this one, and you will find this one. But this is now banned because this we are using generally for anesthetic purpose. But this you will find for any type of organic synthesis you are doing, whether aspirin synthesis or paracetamol synthesis. In intermediate level, you will not synthesize aspirin or paracetamol. But in obviously in your degree classes, you will use more this dichloromethylene. But here carbon tetrachloride you will get in your chemistry lab. So these three you will find in your chemistry lab, but this you won't find. Okay, okay, because it is in a gaseous state. These three you will find it. So now. So we can write it over here because as I told you that I will give notes also. So here we can write alkyl halide. Okay, alkyl halide are colorless when pure form. When it is in pure form. Okay, because whether CH3Cl or CH2Cl2 or CHCl3 or CCl4, they all are colorless. Okay, they don't have any particular color. However, bromides and iodides develop color when exposed to light. Okay, we know that this bromide and iodide developed color when exposed to sunlight. Okay, when exposed to sunlight. Correct. And these are the sweet smell. So these are the physical property for this alkyl halide. Sweet smell. There are many more. Okay. So next point, how the melting point and boiling point trend is following. That also we'll see. MP and BP. Okay, melting point and boiling point. How it is following, that also we'll see here. So it will be like uh, generally the chlorofluoromethane. Okay, some chlorofluoromethanes are gases at room temperature. Okay, mostly the lower, okay, alkyl halides are gases in, or we can say gases at room temperature. Okay, gases at room temperature, RT. Okay, but the higher member, okay, this is for lower alkyl halides. Lower means CH3Cl, CH3Br. Okay, but higher alkyl halides are liquid. Okay, these are liquid at room temperature. Got it? So like that, and this organic, like suppose like few we exception will be there. Like why that is the exception, that also I'll discuss it. This generally alkyl halides are polar in nature. Okay, well, right? Generally these are polar in nature. Okay, generally these are polar in nature. Suppose, see how these are polar in nature. We have written this example: CH3Cl, then CH3. Okay, then this molecule, carbon, hydrogen, Cl, hydrogen, Cl. Then next it is carbon, chlorine, 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 hydrogen. Correct? And then carbon, Cl, 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 and Cl. Got it? So this will be your non-polar. This will be non-polar because the electronegativity direction or the polarity direction will be this carbon to chlorine. Here also like this, here also like this, and this side also it will be like this. So it is cancelling out. Okay, it is cancelling out. Though, like the question will arise like the carbon and chlorine, the bond between carbon and chlorine is a polar, but why the CCl4 is non-polar? Like that question they may ask. So here it is like, okay, we are agreeing that carbon and chlorine, the bond between carbon and chlorine, it is polar because the electronegativity difference is present, because chlorine is more electronegative than carbon. So the polarity will shift this side. But we have all the four chlorine attached to this carbon, so it will cancel out each other, and finally the polarity dipole moment will be 0. So it is non-polar. But in this case the dipole moment is not equal to 0, so we can say it is polar because see the polarity is moving this side, and this side. So maybe 2 chlorine it will get cancelled out, but 1 it won't, right? So what will happen here? The polarity will be existing, right? So dipole moment mu not equal to 0, so it will be polar. Here this also polar. Okay, this also polar. Are you getting my point? Why the polarity? Because the electronegativity difference. But only CCl4 is a non-polar. Correct. So here the intermolecular force of attraction, dipole and van der Waals. Okay, the what type of van der Waals force is attracting over here? Van der Waals. Okay, van der Waals force. What type of van der Waals force is acting over here? It will be dipole interaction. Okay, here the van der Waals force acting is dipole interaction. But in case of alcohol, water, what type of van der Waals force is acting? There it will be hydrogen bonding, but not here. Okay, this hydrogen bonding will act. This is also van der Waals force. So that hydrogen bonding will act on your alcohol, water. It means minimum one sigma bond between oxygen and hydrogen, and this oxygen, fluorine, and your nitrogen. This element only will show hydrogen bonding, and then also They should have minimum one sigma bond with oxygen or with fluorine or with nitrogen. Then only this hydrogen bond will takes place. So that is the fourth type of van der Waals forces. There are four type of van der Waals forces. Out of that, this is the strongest, hydrogen bonding. Okay. Then second in strongest will be dipole dipole. Then dipole induced dipole. Then induced dipole induced dipole. Okay. There are four types of van der Waals forces. Got it? Now already we have discussed the boiling point trend. So this you are going to put it over here down. Okay. Here you have to put the boiling point trends after this. Okay. Then or we can say that order we can write boiling point. It will be like if suppose not only chlorine, if suppose all are alkyl groups, CH3 iodide, CH3 bromide, CH3 chloride, and then CH3 fluoride. So how the boiling point trends will follow? Like this. Here the iodide will have more boiling point than bromide, then chloride, and then your fluoride. Got it? So this is the boiling point trend it will follow. Got it? So again, if you are taking isomer, okay, if you are taking isomer, suppose you have taken this one, this molecule CH3, CH2, CH2, CH2 Br, then CH3, CH2, CH, CH3, and here you have taken Br, and one more molecule carbon CH3, CH3, then carbon CH3 and Br. Okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All are butane. All are four membered only, right? 1, 2, 3, 4. All are four membered only. Only we have changed the position of bromide. Here the first position it is there 1 degree bromide. This is 2 degree bromide, and here it is 3 degree bromide. Okay, we can classify like 1 degree bromide, 2 degree bromide, and 3 degree bromide. So out of this 1 degree, 2 degree, and 3 degree, how the boiling point trends will follow? See, here the boiling point trends it will follow like this 1 degree will have more boiling point than your 2 degree, than your 3 degree. Correct? Got it? How? See, this arrangement for 1 degree arrangement, suppose this is your 1, 2, 3, and 4, and then here bromide is there. See, another molecule clearly you can put it over here. Another molecule. So this is the arrangement, correct? The proper arrangement you are getting. This is the proper arrangement you are getting. See the distance between these two. The distance. Okay. This is the van der Waals interaction. That's why it is stacking like this. For secondary, how this is stacking? Let's see. 1, 2, 3. 1, 2, 3, 4. Okay. This one we don't want. 1, 2, 3, 4. So 4 carbon. Now bromine is here, right? Now tell second molecule will be here. Then bromine will be here. Then third molecule will be here, because we have to provide space, right? Now see the distance. It is increasing, right? And what is boiling point? Boiling point means to break the van der Waals interaction. Okay, to break the van der Waals interaction. That is the boiling point. So when it will break that van der Waals interaction, then the molecule will separate out and it will be its vapor phase. Okay, whenever this molecule, this entire molecule go to the vapor phase, it means what? This molecule will be separated. So this is one molecule. Okay, 1, 2, 3, 4. The another molecule will be somewhere here. Okay, so the distance, separating distance we are providing, we are doing this separation by providing heat, like to heat. We are providing heat and this separation is taking place. So what we are doing, we are breaking the van der Waals interaction. Van der Waals interaction. Okay, so it will be separate. Here you see we need very less amount to separate these two. That's why you see this is primary and this is secondary. See, primary is having more boiling point than secondary. It means primary require more energy to separate out than your secondary. Likewise for tertiary, you just see here 1 and here Br. Now you have to see here 1 and here Br. See the distance? It is still more. So here it will be very less amount of energy it is required, correct? Here the less amount of energy it will require. So that's why secondary will have more boiling point in comparison to tertiary. because it is required less energy to break this van der Waal interaction. Correct? Got it? So we can write it over here, like how we are going to write it in a language. We have to write the boiling point. Okay, the boiling point of isomeric haloalkane decreases, okay, decreases with increase in branching. We have already discussed, right? So those examples you take and put it over here. Correct? Put it over here. Those examples you take it from there to the isomeric and put it here. The second point, after this example, you can write second point. Boiling points of isomeric dihalobenzene. Okay, boiling point of isomeric dihalobenzene are very nearly by very nearly the same. Okay, so we are just talking about this molecule. So this is your, okay, ortho position, the orthochloro or 1,2-dichloro. This is your 1,3-dichloro, 1,3-dichloro, and this is your 1,4-dichloro. Okay, so how the boiling trends it will follow over here? How it will be? It is not like this is, it will be your more boiling point, this ortho. Okay, ortho will have more boiling point over here. Okay, so I'll just write ortho will have more boiling point. Then directly it will go to your para. Okay, after para it will be meta. See, the arrangement will be there the interaction will be there with the chlorine chloride. Then your meta, it is not fitting in a crystal. Okay, it is not well fitted in a crystal, but this one is very well, it will fit it over a crystal. So that's why it's having more boiling point. It is very less boiling point. Okay, so we can write, however, the para isomers are high melting. Okay, however, the para isomer are high melting point. This is boiling point. Okay, this is boiling point trend. High melting point as compared to, okay, as compared to their ortho and meta isomer. Okay, if melting point trend, if you want to see, it will be, it will follow like your para will be having more melting point, then your ortho, and then your meta. Meta will have the least melting point. Okay, so meta isomer, because why it is having para isomer is having more melting point. Okay, why para isomer is having more melting point? It is due to the, okay, due to the symmetry. Okay, due to the symmetry of para isomer that fits, okay, that fits in crystal lattice. Okay, crystal lattice better as compared to ortho and meta, ortho and meta isomer. Are you getting? Ortho and meta isomer. So here, as I told you, this is fit very well in a crystal, because see the chloro in the this extremist, and this side the chloro is in this side extremist. Okay, but here the chloro is like, it is opening like a flank, right? So now what will happen if you take another molecule of meta chloro, meta dichloro, then it won't fit very well. Okay, the distance will be more between two meta dichloro, but para dichloro, the distance will be very less. Okay, it will be like very closely associated. If it is very closely associated, then the van der Waal interaction will be more. So it will require more energy to melt. Okay, to getting, okay, to melt. The next concept is your density. Okay, density. How density will work over here? That we'll see. It is also depending on your boiling point. Okay, so bromo, iodo, and polychloro derivatives of hydrocarbons are heavier than water. Okay, and whichever is heavier than water, that will be having more density. Okay, and that is depend on your molecular weight. So bromo, iodo, and polychloro. Okay, polychloro derivatives of hydrocarbons are heavier, okay, are heavier than water. One example I'll tell you. I don't think so in your intermediate that type of reaction you have done in your lab, that we call binary separation. So this is your flask. Okay, this we call separating flask. Okay, here one lock will be there, like your burette, and here the cap will be there. Here we are pouring that binary solution. Binary solution means aqueous layer as well as organic layer. Okay, aqueous layer and organic layer, both we are pouring. Now suppose aqueous layer will be always water, H2O, right? If organic layer you have taken any of the chloro, suppose you have taken DCM, okay, DCM, dichloromethylene, or chloroform if you have taken. So what will happen? Your DCM, like after shaking this after shaking this separating funnel, what will happen? It will form a layer. Okay, because water, aqueous layer and organic layer won't mix up. Correct? So now what will happen? This DCM will be in the lower side and this water will be in the upper side, because this DCM density is more. If this density is more, it will go to the lower side, and if this density is less, it will go in upper side. So that's why bromo, iodo, and polychloro derivatives of a hydrocarbons are heavier than water. So if it is heavier than water, it means this density is more. So if density is more in the separating funnel, it will be at a lower side. Okay, and this will be your aqueous layer, and this is your organic layer. Okay, this will be your organic layer, this will be your aqueous layer. Okay, so you got it. So likewise, the solubility. We have the solubility. Though we know that alkyl halides are very least soluble, or it is insoluble. Like if you are taking carbon tetrachloride, it is insoluble in water. But if you are taking chloroform, okay, then slightly soluble we can say. So we can say in a statement, the haloalkanes, okay, the haloalkanes are very slightly, okay, slightly soluble in water, but they are readily soluble in a organic solvent. Okay, okay, but they are readily soluble, they are readily soluble in organic solvent. Correct? In a organic solvent. Correct? You're getting. But here one more concept you can say why it is not soluble in water, because see, and it's require energy. Okay, it's require energy to overcome the attraction between the haloalkanes molecule and break the hydrogen bonds between water. So two things it should be happen. See, suppose you have taken this molecule CH2Cl2 and you have taken water molecule. There are many water molecules. Suppose water molecule, water molecule, water molecule. Likewise, there are many molecule of CH2Cl2, CH2Cl2, CH2Cl2. Now to get soluble, this is having in one beaker, and this water is having in another beaker. Now I want to mix it, and if it is dissolving, then we call it's a soluble, right? So how this thing will happening? See, we know that this CH2Cl2, CH2Cl2, all dichloromethylene is having the van der Waals interaction. Okay, like dipole-dipole interaction it will have in between. So to get dissolving, we have to first break this bond. We have to first break this interaction and to make a new interaction with water. So for this, what we need? We require some amount of energy, correct? Likewise, here also, see, with this oxygen, this hydrogen will have hydrogen bonding. With this hydrogen, this oxygen will have hydrogen bonding. With this hydrogen, this oxygen will hydrogen bonding. This hydrogen will have hydrogen bonding with this oxygen. Okay. So likewise, this hydrogen will have hydrogen bonding with this oxygen. So here the hydrogen bonding is there. So we have to break this also. This is hydrogen bonding. So you have to break this bond also, and that is also require energy. So now here the energy required is more. Okay, so correct, to break this van der Waal interaction it is required less energy, but to break this van der Waal interaction it is required more energy. Here it is less energy, correct. So here with the organic solvent it will readily dissolve, but in if you are want to dissolve in a water, then it is highly impossible, right? It won't get dissolved. So that's why it is a slightly soluble, not readily soluble in a water. Okay, because we have to break this kind of van der Waal interaction also. Okay, so this is the explanation over here. So now with this we have completed the physical properties. Here next will be your chemical reactions. Okay, next will be your chemical reactions. So if you are liking these classes and if you want more like these classes and if you want complete notes or for your 12th standard, see my motivation is only to reach these classes to the maximum. Okay, if you are watching, if someone is getting help with these classes, then my job is done, correct. So and if you are not watching and if it is not circulating to the maximum people, whoever is the needy person, then somewhere my ambition is like diverting. Okay, so to get the motivation, I should know that you are watching these classes and whether you are facing any kind of problem. So please do comment. If you are liking, then also you can comment it. If you are not liking, if you want anything add, like anything should be added more, okay, then that also you can comment it. Okay, so based on that I will modify my classes, correct. So thank you very much.